right, so let's see if we can do the reverse of what we did yesterday. Here's an expression for the acceleration as a function of time. Assuming that this object has a velocity of 6 meters per second at time t equals 0, and that it starts from the origin, find an expression for v as a function of t and x as a function of t, where t represents time in seconds. Everybody understand what my question is asking? Now, before I let you guys kind of go off and work this real quick and see if you can do this based on what we've talked about in class, what are the units of the 6 and the 9 here? I know they're constants, but I asked what are their units?
Meters per second squared.
So 9 would have to be meters per second squared. Would have to be. For it to be an acceleration that would be acceptable where a velocity is 6 meters per second, right? So it suggests meters and seconds are going to be our units. And since that's an acceleration, I would expect the units for 9 to be the units of acceleration. But what would the units have to be on the 6 then? Meters per second cubed, correct. So when we think about units, they may not be written in a function, but there's an implication that these two numbers have units. Right, that's kind of implied here. Everybody okay with that? We wouldn't write them into the function. They become distracting. All right, see if you can answer the question. I'm just curious, and I'll check everybody as we go. So let's talk a little bit about the difference between what we did yesterday and what I'd like you to do today. Consider working this problem in the other direction. So I want the velocity function. I'm going to use this antiderivative pattern. First thing it does is tells me to take my value for t, which is t to the 1 power, add 1 to the exponent, t to the 2. Now, I then have to divide by the new exponent, which is 1/2, but there was already a 6 here, so that has to be 6 divided by 2. Move on to the next term, minus. This is t to the 0 power. So I add 1 to the exponent, t to the 1 power. Divide by the new exponent, which is just 1. However, I have a coefficient in front, so I have to put the 9 down. Now, I'd say we're done here, but we're not. Something I brought up yesterday that I need to remind you about today is that had there been a constant here when I took the derivative, it would have disappeared. So I have to consider the fact that there is the possibility of an initial velocity, a value for my function when the function variable is 0. Now, I gave a number to use of 6, but start with the constant. Now, I should write my expression more clearly. So v is going to be 6 divided by 2, 3t squared, minus 9 divided by 1, 9t, plus 6. That's my expression for the velocity using the conditions provided by the problem. We call this kind of condition a boundary condition. Bless you. Or initial condition. I will often use the word boundary condition, though. Now, that just gave us velocity. I would like to go further and find position. Now, I do believe that this is something that we can kind of do most of it in our head. I don't think I need to write everything out. So I'm going to try and do more of this in my head. T squared becomes t to the 2 plus 1, or 3. And 3 divided by 3 is 1. So I'm good with that. Minus. T to the 1 power becomes t to the 2 power. 9 divided by 2 is 4.5, or 9/2. Plus there is no t on the 6. So it's implied that it's t to the 0 power. So that becomes t to the 1 power. And 6 divided by 1 is 6. Then I must put in a constant to represent my boundary condition. Where is the object at time equals 0? My problem, however, tells me that the object starts from the origin at time equals 0, suggesting x naught is 0. So when I'm all done, I have x equals t cubed minus 4.5 t squared plus 6t. My velocity is 3t squared minus 9t plus 6, and my acceleration, which began all this, was 6t minus 9. I generated 3 functions from just knowing the acceleration. This function is the slope of the position graph, and this function is the slope of the velocity graph. Calculus is the algebra of functions. So, in continuing this, tuck these to the side, there's a number of questions I would expect you could answer. For example, could you tell me where's the object when it is stopped? Could you tell me how fast it's going when the acceleration is 0? And could you tell me the acceleration I can ask a number of questions about the motion of the object. These questions are related to you understanding what you have to figure out in each case. For example, where is the object when it is stopped? I can only answer that if I know when it stopped. But what does it mean to say it stopped? What variable am I giving you when I say it stopped? Go ahead. Velocity. So I'm asking you to figure out t that will make this 0. That's when it stopped. And then I can use that here to figure out where it is when it stopped. Try these for just a minute. See if we can't practice it. Work with the people at your table. I want to walk around. If there's any of these that give you trouble, mathematically or something, they shouldn't be too tough, but they might be. Let me know. All right, so the minutia of doing this gets pretty, tedious after a bit. Did we figure out that t equals 1 and t equals 2 for v equals 0? Right, so that gave us when the object is stopped. Doesn't tell us where the object is stopped. For that, I have to plug it in here to figure out where the object is when it's stopped. All right? So just a lot of plug and chug here. Does anybody need me to do that? Did most of you realize that, well, x is at 0, definitely when t equals 0, because it's in one of the boundary conditions, right? So how the acceleration when the object passes the origin, one of the accelerations is -9. But there's 2 more possible times, right? Because it'll be the root of t squared minus 4.5t plus 6. We may need to figure out those two times. So I factored out 1t, but there's still a couple t's left. You guys remember how to find the zeros of a function, right? Now, this is not particularly useful for my class. I'm asking because it's one of the things you could be asked to do, but this is just tedious kind of work. So I would expect if you know how to use your calculator to do this, use your calculator to do this. I don't want to spend a lot of time with the algebra minutia. It's not worth it. But other questions I think are pretty clear, like finding out when the acceleration is 0. That's not hard to do. You're going to get 1 time. The acceleration is 0 at what? Looks like 3/2. And then plug that in for how fast it's going at 3/2 seconds. Do you need another practice, or do you feel like you guys can accomplish your homework tonight? Your homework is 5 of these, and they're of this level of difficulty. All okay? I would like to talk a little bit about the phrasing antiderivative for a minute, and have you understand that what we're doing is playing fast and loose with the rules. So I'm going to take one of these functions, and I'll probably take this function because it's the simpler of the two to explain this to you, okay? Understood what we were doing over here, then you'll be fine. And to put it what we needed to do here, you're fine. Kind of bluntly, this way is derivative. This way is antiderivative. And for this direction, you need initial conditions. If that's all you want to know, that'll get you through the first test. Won't get you through the whole year, but it'll get you through the first test. Okay? And it seems from talking to you guys, you're okay with this, at least for polynomials. For polynomials, the derivative side, xn equals nx to the n minus 1. And the derivative side, the antiderivative side, antiderivative becomes 1 over n plus 1, x to the n plus 1. Right? Our two processes from moving along this chart. You're fine. And if you could do it, you're okay with just this. Taking the derivative, do this function. Taking the antiderivative, do this. You're good to go. And just don't forget your boundary conditions. But I want to make sure, over all the top of this, I remind you that this is only going to work for you for polynomials. Polynomials of basic powers. We do anything else, we start having trouble. Anything else. For example, there are things we can't do with this. What if I tell you that the acceleration is 5 divided by x? Can you try and come up with an expression for velocity? You're going to have a problem. If you don't see what that problem is now, I'll be very clear. This is 5x to the negative 1. If I attempt to use the polynomial rule, then I would have 5 divided by negative 1 plus 1, x to the negative 1 plus 1. Do you see your problem? Can't do it, can we? This does not obey the polynomial rule. And of course, if I give you that the acceleration is equal to 5 cosine 2 times t, you understand all bets are off now, right? That's not a polynomial. You don't have anything like this. So, well, we can't do this. However, you're eventually going to have to learn those rules too. So we got it? So those rules are coming. We'll just do the polynomial rule for the first test, and then every time we need a new rule, we'll learn it in time for that unit. Does that make sense to all of you? So we won't learn a lot of these for a while. We'll simply practice these for a little bit. All right. So from the homework, problem 1A. velocity equals 3t squared minus 24t plus 36. I want position and acceleration. And I tell you that at time 0, the object begins at the origin. So I think you've got something you can work with. Let's start with just finding the two functions. I'll find the position vector or the position function first. That's doing the antiderivative. So add 1 to the exponent, divide by the new exponent, gives me t cubed. Minus, add 1 to the exponent, t squared, 24 divided by 2 is 12. There is no t in the 36, that's 36 to the 0 power. So place a t there, 36 divided by 1 is still 36. And it tells me that my position at time 0 is 0, so I don't need to add anything to that. That's the position function. Finding the acceleration from the velocity function is the derivative. So I'll take the derivative, bring the 2 out front. 2 times 3 is 6. 6t to the 2 minus 1 is just 6t. Go to my next term. That's 24t to the 1 power. Bring the 1 down front. 24 times 1 is 24. T to the 1 minus 1 is t to the 0. I think that's my acceleration function. So those are the two functions for part A. Then find the position when the velocity is 0. So 0 equals 3t squared minus 24t plus 36. Let's simplify that to make it t squared minus 8t plus 12, I think. I think we'll go with factoring because this looks like it factors. Can I use 2 and 6 as my factors? So with that, I find that the velocity is 0 when t equals 2 and when t equals 6. They are both positive. So if I want to know, find the position when the velocity is 0, I need to find v at 2 and v at 6. Would you guys be okay if I didn't do that and you just plug it into your calculator? All right. And then find the velocity when the acceleration is 0. That looks a lot like when t is 4. Just solve that, set that equal to 0 and solve for t. And then I want the velocity, so I'll plug it in there. You guys okay if I don't plug the numbers in? All right. The truth is, when we have acceleration equals 6t minus 9, we actually have what's known as a differential equation. Because A is considered a differential. You've learned now two differentials, but you didn't know there was a word for it. But any variable that can be written as a derivative is considered a differential. So acceleration can be written as a derivative, therefore its differential form is dv dt. Velocity is also a differential. It can be written as dx dt. In fact, you could argue that acceleration is actually two differentials. Right, if I substitute in for v, I'd get two differentials there. Wouldn't you guys agree with that? In fact, there's a symbology to go along with this. Acceleration is considered the second derivative of position with respect to time. These are the differential forms of these variables. So, in the function I have right here, I can write this as a differential equation by replacing A with its differential form. Now, this is not a particularly interesting differential equation, by the way. Most of you who will go on into technical degrees will take a course on differential equations. And truthfully, differential equations occur frequently in nature. There are a lot of times when an object's behavior is based on the rate of change of other variables. So we see it a lot in nature. Now, for those of you who do pursue that, you'll find that calculus becomes the arithmetic for differential equations. You learn calculus so that once you start doing differential equations, you have a tool chest worth of arithmetic. In the same way, actual arithmetic became just something you did while you were doing algebra. So you will be building up these skills that each one builds on the next. But what we've been doing is saying, okay, if I want to find v, I just find the antiderivative of the function. That's really not what we're supposed to do. Technically, if I'm trying to find v, I'm supposed to go through a process that involves taking the integral of the function. Now, I'm not going to spend a lot of time with this idea here because you have an entire calculus class to do so. The reality is, what we're supposed to do is solve this as a differential equation to get v. And that is kind of a three-step process. And I want you to be smart people, but I also want you to understand that there's something bigger here. The process involves splitting the derivative, meaning multiplying both sides by whatever's in the bottom. A step we don't have to do between here and here, which is called collecting like terms. I say we don't have to do it because the rule means to get anything with a t on the same side as dt and anything with a v on the same side as dv, but that's already been done. So I don't really have to do anything to change that. And the last step is to integrate both sides. This symbol is the integral symbol. And what it actually means is to sum. It is just a fancy S used in place of the summation symbol. You guys do know the summation symbol, correct? Because you've had Algebra 2, so you're aware that summation is capital epsilon. So this symbol is just a replacement for epsilon because it is a summation. Now, it should be noted that when you are taking the integral of a function, one of the steps in the integral is to perform the antiderivative. That is one of the steps. So although I'm saying we're taking the antiderivative, we are doing so much more than that. I'm just leaving out all of this math. The truth is the left side has to have the antiderivative found as well. But since there's no v there, we say this is v to the 0 power. When we take the antiderivative of v to the 0 power, we get v to the 1 plus a constant that represents the initial velocity. The right side is also supposed to be evaluated, meaning we're supposed to evaluate it, meaning putting in where our starting and where our ending points are. These are just things we're leaving out. Now, I'm not expecting you to have this skill. I'm not even expecting this to be on the next test. I'm talking to you about this because we are playing fast and loose with these rules. Eventually, we will have to deal with differential equations. Eventually, you will have to deal with the concept of the integral. I'm going to teach you some things about it, but I'm going to be always at the surface giving you just the basics. I'll let your calculus class do the rest. Does that make sense to all of you? So just be aware, and I'll be honest with you, the only reason I'm even talking about this stuff is I have people in the room who are in or have passed calculus, and I feel like they deserve to have a moment where we talk about the fact that I am aware that I'm playing fast and loose with the rules. You follow me? But yesterday, I gave us, mostly starting with position functions. So something like 2 2t cubed minus 3t squared plus 2 or something like that. And I asked you to find the velocity and then the acceleration. You guys were largely successful in that when you went to find the velocity, you know to bring the exponent down, multiply it by whatever coefficient is there. So 2 times 3 is 6. And then subtract 1 from the exponent. T to the 3 minus 1 is t squared. Move on to the next term. Bring the 2 down. 2 times 3 is 6. T to the 2 minus 1 is just t to the 1. And since there is no actual t there, we can say that it's t to the 0 power, which is just 1. Bring the 0 down, it wipes everything out, and I have no term there. Go to the acceleration, I take the derivative again. Now remember, v is dx dt, so we are finding the derivative of position to get velocity. Acceleration is dv dt, so we are finding the derivative of the velocity to get acceleration. Bring the 2 down, I get 12t to the 2 minus 1, which is just t, minus, bring the 1 down, 6 times 1, 6, t to the 1 minus 1, t to the 0, and that's my final portion of my function. All good? Now my expectation is you could work in either direction. It's just a little pattern. The pattern isn't a big deal. So if I want to go from 12t to the velocity, well, I'm going to have to add 1 to the exponent and then divide 12 by the new exponent. That would work backwards, right? That's working it backwards. And the wording, antiderivative, belies a little bit of complication that's actually being ignored by us right now. So let's follow the argument here.